Welcome to video 11 in a series of introductory videos for InventorCAM. This video's topic is HSS Xpress. So the title HSS Xpress refers to the HSS toolpath, but in the basic version of it, available in some of the North American packages that we sell. And it is a toolpath that is available with all the packages. No matter which one you get, you always get these two versions of HSS that I'm about to show you in this video. So let's take a look at how that works. So I have it set up for these taper faces on the back side here. So I'm just going to go add milling operation, HSS. So HSS Xpress refers to parallel cuts, linear, and constant Z. These two operations, these two technologies inside of HSS. In video 12, we'll take a look at the rest of these in the HSS full video. But for now, we're going to look at parallel cuts, linear. So you start by choosing your coordinate system. You can see here I have it auto-populated. Let's go to geometry. And HSS is a surface-based toolpath, meaning that instead of choosing contours or edges or anything, we're going to actually choose faces or surfaces off of our solid, off of our design model. So let's go ahead and do that. We'll do drive surface. And I'm going to choose just this surface here. You'll note that there's actually some slots in there, so these gaps are going to come into play here when we actually start adding things to the toolpath. Now, you choose the surface, but the surface edges can act as a boundary. You can see in the bottom left corner now, the toolpath, the red toolpath, stays away from the edges of the blue surface, and that's because we're avoiding the edges, the exact edges. So that acts as a boundary. The tool diameter stays completely inside the surface edges. I'm actually going to switch this to the second option, meaning that I take the toolpath right to the edges of the surface. So it still acts as a boundary. It's not going to machine anything outside those surfaces, but it allows the tool to maintain a tangent point and go as far out as possible. And that's useful for things like ball mills, bull end mills, even lollipops. If you do undercutting with HSS, then you can actually tell it to go around the surface as much as possible, machine all the surface to completion while still maintaining the tangent point. So it's a good way to make sure there's no burrs or anything like that at the edges of your surface. The other option here is really just to limit the motion of the tool by 2 points. So once you do this, you'll actually have the ability to choose points on your surface, and in the direction of the toolpath, you tell it where to start and where to end. And it basically is just a way to trim the toolpath between those 2 points. Well, let's just put on the second option there. Drive surface offset is our way of basically turning this into either a overcut, undercut, or if you could think about it like a roughing cut. You're basically telling it to leave material or go deeper into the part, but in the direction of the normal of the surface. And the normal of the surface, depending on if you take a look at this or not, that yellow arrow represents the normal of the surface. That's essentially just perpendicular to that point, to that surface. So it's just a direction of the surface. So any kind of offsets or anything like that are not in the Z direction, they're in that direction. Now, we're in parallel cuts linear, so we're going to actually define the angle that the tool will take as it travels along that part. And you can see my x-axis positive is in the long direction there, the long side of the part. So it's actually this direction. And that is 0 degrees. This value is a degree off of the positive x-axis. So right now we're just going to go zigzagging back and forth across the part in that direction. If I didn't know what angle I want to put it at, I can choose line and choose 2 points. 2 points define a line. It gives us the angle from the x-axis, and it's just a way to use the geometry to drive things. So we don't actually have to plug in an angle. We can just read it right off the geometry. Okay, so let's go with 0 degrees. Let's go to tool. And tool selection, tool definitions were covered in video 2, so I'm just going to skip over that, and we'll go right to choosing just my 1/4 inch end mill. Feeds and speeds under your control, under data. And there's actually a feed control option as well. So you can actually denote areas where you want to change the feed rate depending on different features. So you can define the control area using a sketch or edges, and you can tell it exactly how to control the feed rate. And of course, as always, coolant options. Now, what's unique about HSS is actually you can choose any shape of tool, shape tools, or some of the defined, the standard definition tools as well. And I mentioned earlier, undercutting. So this is the only toolpath that can do undercutting. It's all based off of the shape of the tool. So it's maintaining that tangent point with whatever shape of tool, whatever cutting surface you've defined on your tool with the surface you selected in your geometry section. Under levels, we'll see that it's different from the other toolpaths in that it doesn't have an upper level, lower level, or a depth or anything like that. It just has a clearance area. That's because HSS is predominantly for finishing. There are roughing options in this toolpath, but mainly it is a surface-based toolpath because you're going to go in there and finish a surface. So because of that, there is no need to start at a certain level and go down to a certain level. You just go right down to the surface, and you have the control over the clearance area to a plane. Now, you can actually tell it whichever plane you want it to be in, and whatever height that plane should be from the origin in that area, but that's really just what you have control over, just where to clear to. If you were doing, let's say, a wall and you wanted to clear into a plane in the X direction, we can just give it a X height or an X coordinate, and then it would clear to that direction rather than up in Z every single time. This can be useful if you're doing any kind of undercuts as well, where you want to retract away from the part rather than up, because obviously if it's an undercut, up is probably not a possibility. Other levels you have are the safety distances and the retraction. So again, it's just a matter of just clearing the part. It's not where to start and where to end. Toolpath parameters. Because this is a very basic toolpath, all we have control over here is really just the step over. Now, because I chose a ball end mill, I have control over the step over as either the actual value or what scallop height I like to leave behind. If you take a look at this value in here, as soon as I put in some sort of value, I'm just going to put in something at random, you'll notice that it generates a step over to tell us what that maximum step over should be to achieve that scallop. So you can actually control this by the scallop height. If you know the finish you're looking for, the RA value or the RMS value, you can calculate what the scallop height should be from that and then plug it in here, and you'll get the exact step over you need to achieve the finish called out on your print. I'm just going to set this up as a 20 thou step over. Everything on the top half here is to deal with the fact that sometimes you're dealing with a translated surface, maybe something from a customer's part file, an IGES file, step file, and that sort of thing. So all these tolerances on the top half here are really just to kind of fine-tune the toolpath so you reduce data points, so you're not really driven by the surface completely, because it might be a bad surface. There might be some erratic data in those data points, those surface points. So you might want to just kind of either fine tune it or make it a little coarser, so you don't actually have to deal with a bad surface that is in the design side and then machining that. Under sorting, we basically tell it what our cutting method is. It's the direction the tool is going to take along the part. So it defaults to zigzag, which means it'll alternate between climb and conventional. That might actually not lead to a good surface. So you might want to just do one way, meaning that now you can tell it to either do climb or conventional or clockwise or counterclockwise. So this leads to a better surface. Now, but what this does, though, is it means that you're going to constantly be retracting and repositioning to continue that one-way cut. If you have a closed surface, let's say you're doing a circle feature or a dome or something like that, where the surfaces meet each other, then one way means that it is a continuous movement. You actually can get it to just start and stop at the same position. Cut order, either standard, which basically means from one side to the other, from the center away, or from the outside to the center. Those are your options. Under machine by, we have lanes and regions. If you look in the bottom left corner, right now we're doing lanes, so it continues the toolpath across any gaps. So you can select as many surfaces as you want. They don't even have to be touching, but just be aware that there will be air cuts there as it passes along there. Or we can set to regions, where it'll recognize that there's a gap there, and then just set this up into separate regions. And instead of jumping around in between these two, it'll do one and then jump to the other one. But in our case, let's leave that as lanes. Your cut order being standard, if it goes from one side to the other and you don't like it, you'd rather go the other way around, reverse it, you can just do a flip step over. And what that does is it just basically reverses the direction of the toolpath. And then start point, you can actually define a point on your part where you'd like it to start. Under modify, again, we have some other tolerances here to further define the toolpath so that it's a little less stringent to the translated surface, if that's the case. And on the right side here, you have some actual modifications. For instance, under round corners, if the surfaces you selected have have met at a sharp corner or a radius that's smaller than the radius of your tool, then it's going to try and approximate that by doing this kind of weird triangular motion here, just to get as much of that surface machined as possible. Now, that's probably not going to make any sense. You don't want to bury the tool, or you don't want to leave a feature that kind of looks weird like that. You want to smooth it out. You can click on round corners and plug in the actual radius you'd like to leave behind. So it's not part of the design, but in the code, in the toolpath, you can get it to actually leave behind that radius, and that can smooth things out and make it a lot more better in finish. Trim/extend in the direction or on the side direction of your toolpath, you can get it to just extend the toolpath further out or trim it back based off of whatever value or percentage you put in here. Sometimes that could be used as a lead in, lead out on the edges, depending on whatever it is you're trying to do. The HSS toolpath is very versatile in that way. There's ways to do your particular feature with all these different options in here. Tool control is not actually something you're really going to control in this particular toolpath. This interface is used in the 5-axis toolpath. So there's a lot of stuff in here that carries over, but because the interface is the same, we have this one here. Under link, you have control over where it will approach and retract at the beginning and the end of the toolpath. You have the different options in here. So you just choose the level that you'd like to go to. And you can choose to use a lead in, lead out if you like. Under the links tab, you control what happens inside of the toolpath. Once you've entered into the part and you're going along, if there's a gap along the cut, in this case, let's say in this surface here that we're about to do, those two slots will be a gap. So what will happen once it encounters that gap? There's a discontinuous surface. What will happen if it needs to jump over that gap? It goes to the clearance area. If it's a small enough gap, then it'll just continue along the toolpath. It'll just continue the feed motion. And determined between small and large is just this value right here. You either put in a percentage of the tool or a value. You can add a separate feed rate for any kind of connections or any kind of lead in, lead out that you've added there. For link between slices, that is essentially what happens for a simple surface like this at the edges. So as it's going across, it gets to that edge. If to reposition and begin the new path, if it has to do a small move, then it'll just go direct. It'll just kind of just do a simple line and then continue the toolpath. But if, say for instance, on a toolpath on a surface like this that has this kind of angled edge, those movements might seem large to reposition. So it would actually go to the clearance area, reposition, and then begin the next path. So you have, again, controls over where that, how that actually gets done in both the large gaps and large moves. Does it go to the clearance area, or does it follow any one of these options here? This particular window, I usually suggest that you start with the default options. That way, if there is something that it recognizes as a gap or that it recognizes as a link between a slice, it'll go to the clearance area. It'll be really apparent that it's doing that. And then you can decide if you need to go to the clearance area or if you want to use one of the other options to kind of smooth out the toolpath. And we're going to see that with this surface. So I'm just going to go to the next option here. So there's a lot of references to the lead in, lead out. To actually define it, we go to default lead in, lead out. You can see there's many three-dimensional options here for lead in, lead out, and this just becomes the default. So let's say I want to use a lead in, lead out on my small gaps. I can say use lead in, use lead out. If they're the same, I can just say use lead in, lead out. Now, as soon as I do that, I have the option of just using the default, or for this particular surface, this particular toolpath, I can just uncheck that box and tell it which one specifically I want it to use on the small gaps of this surface. So there are defaults defined here, but then there are ones where you can individually choose what it's going to do. Now, in the geometry section, we told it to machine certain surfaces. We told it that in our drive surface geometry. But there might be nearby surfaces that aren't known by the toolpath because it only focuses on what we tell it. So in the drive surface, it knows that it needs the machine, and the gouge check will tell it what we want it to avoid machining. We want it to avoid colliding with. So you can check collisions against any surface that you choose here. So in this case, the drive surfaces are the ones we chose in the geometry section. Check surfaces we choose here. So if I click on new geometry, I have the same surface selection interface that I have before in the geometry. Here I'm just choosing surfaces that I do not want to touch. So I can individually choose them, Or I can come over here and say all faces adjacent to the drive surfaces, meaning any surfaces that were in contact with the ones that I chose. So since I chose this surface here, it basically will choose the walls of the slots and these fillets here. So you'll notice it's anything that's directly touching, directly adjacent. So that's why I would probably have to go and manually choose some of these other guys because they're not in direct contact. And those are just surfaces that I do not want to machine. We can check those surfaces against items in the tool. So the tool tip, the tool shaft, the arbor, and the holder. If I had defined those things, I can make sure that those stay within a certain distance away from the drive surface and the check surface, making sure that they don't even penetrate those, causing a gouge. Now, if there is a collision between those two, what is the strategy to remedy that? Well, under strategy, we have 4. We have retract tool, trim and relink toolpath, stop toolpath calculation, and report collisions. Each one of those does something a little different. Retract tool retracts the tool in whatever direction you tell it to go in. By default, it's the tool axis, and for a 3D toolpath, that's going to be the Z-axis. But if you were doing an undercut, or if you were trying to avoid a particular feature, whatever reason it is that you want to go in a different direction, you have these different directions that you can retract in. Trim and relink toolpath simply recalculates the toolpath by taking out the bit of code that is actually causing the collision. So in the case of this left side here, if it's going across, it's about to hit that surface, it actually repositions and then just keeps repositioning around those features, around the check surfaces. Stop collisions simply will just, during the calculation, will stop, give us an error saying that there is a collision that we need to fix, and it will not calculate the toolpath. And then the last one will fully calculate the toolpath and just report that there were collisions. In the roughing and more section, for HSS Xpress, you're really just going to get the multi-passes. So you can actually just tell it, in addition to going right down to the surface, you can add additional passes. So this is what I was referring to before as kind of a way to turn the HSS into a roughing toolpath. You can give it some step over or step down, depending on the direction of the surface normal, and you can get it to kind of rough out the part. So this is the only 3D toolpath available in some packages. In the 2.5D Standard and 2.5D Pro, you don't get 3D toolpaths, you just get this one, which is the only 3D toolpath you get. Now, let's generate that toolpath and take a look at it. Okay, so as you see, I have it set to one way, and that's why it's trying to reposition every time it does a pass. Now, if you're trying to have a good finish, you might need to do that. Now, I don't want to do that, so I'm going to go to Toolpath Parameters, Sorting, and I'll just put this back to zigzag. So obviously, as it zigzags back and forth, these little movements over here, it just links them, and it just continues on. So it looks like a smoother looking toolpath, but just be aware that because it's zigzag, it's alternating between climb and conventional. But what we're seeing on the edges here is some link between slices, because it's getting to the end of those surfaces there. And some of these are actually gaps along cut because of the fact that as it's zigzagging, the next pass is actually right over there. So how do we handle that? Well, we're going to go back to links, and we'll do what we mentioned before. So gaps along cut, I'm going to tell it to follow the surface curvature so that the feed move that it does stays in line with the toolpath. And I'm actually going to do the same thing with links between slices as well. So now you see it smooths out the toolpath a lot. So it has one entry, one exit, and it just kind of smooths around the toolpath. If we go back to geometry, still in linear, let's take a look at what happens if I set this to 90 degrees. So 90 degrees from the x-axis. Basically, it's going in this direction now. This one actually might be the better one because this is a long movement of the tool, but as it gets to these gaps, the slots, it actually continues to do the feed move. This could be the case where maybe I haven't machined those slots yet, so I still want it to feed across there so it finishes that surface so there's no real burrs or any kind of discontinuity between the edges there. So it's just a good way to account for the surface. There is a training video on the YouTube channel where I show you how to cap that surface if you really want to completely machine that surface without worrying about the slot. Now let's take a look at the other option available, constant Z. So where linear was going back and forth along a particular angle from the x-axis or along the direction of a line, constant z actually follows the z-axis. It slices up the surface in the z direction, and we get what's almost like a waterline cut. So let's take a look at that. So if you go to geometry, you're still choosing just the surfaces, but there really is no other options there. That's because, again, it's just in the z direction. There's really no way to change it. It's a waterline cut. This actually is somewhat of a better toolpath if you're doing more vertical or near vertical surfaces, because you can actually control it so that it's always moving in the z direction. And if there is a surface that is not in one particular direction, then constant z allows you to kind of slice it up in that same level, so you actually get toolpaths that change direction. It's not just in one direction, you can do curves and such. So everything else here is approximately the same. I'm just going to do a save and calculate. And you'll see that the step over looks like it's a lot larger. But that's only because this is a step down in Z. This is no longer along the surface. So we take a look at this on the side. It is still moving 20 thou in the Z direction, but because the angle of the surface, it actually is fanning out a little bit. So that's the difference between linear and constant Z. So it's usually an interplay between the two. You want to make sure that you choose the one that matches the surface. A lot of this being driven by the surfaces means that the surface controls everything. Any questions of this or anything else from SolidCAM, just give us a call at 1-866-975-1115, extension 2. You can send us your parts or your questions via the ticket system at solidcamsupport.com, or stay tuned for the rest of the videos in this introductory series. Thanks for watching.